Hello everyone. My name is Shirui, and I'm based in Melbourne, and I also work in the Earth observation team with Rory. So today we're going to talk about a presentation that I was giving at Locate 24. And we were at a session called Water the Future, which was hosted by someone from the EOWater New South Wales, and who was also our clients for this project. And our mission we got was to get them an efficient retrieval of the unfarmed water storage area across the region of interest and also across a very long time. So, I'll give some background here. So the unfarmed water storage is quite important because it serves as a very vital resource buffering against the changeable climate patterns and also ensure the agricultural resilience in the water scarcity challenges. So our objective here is to track a total of about 1,500 unfarmed water storage area time series change. The time we're talking about was over 35 years with all the available optical satellite images that we can find from Google Earth Engine. And the region of interest is across the northern valleys of New South Wales. So I have a map here to show the entire area. And the yellow shaded polygons are each of the unfarmed water storage that we're interested in. So all the data that we deliver should be free from the cloud contaminations and all free from the low quality pixels. And this workflow needs to be automated. It can automatically reproduce the results once there's new satellite images available, and we can push that to update the data set. It's going to present within DCC EOW New South Wales. So the platform we're going to use this Google Earth Engine because GE has access to planetary scale of satellite data, and it's also has the capability of the image processing and computation on cloud. So what we are seeing here with figure 1 is that we have our unfarmed water storage base map, which was provided by our clients, and it contains a total of about 1,500 storages, which means that we have 1,500 of polygons. So with our old processing method, which is we call it vector-based processing, which is to intersect each of the satellite image with this unfarmed water storage base layer map to calculate the water area within each of the storage polygon. So what we are seeing from figure 2 and figure 3 is that the black and white map you are seeing are the satellite retrieval from 2 days. And you can see that in figure 2, on the day that we observe this satellite image, we have the water filled up on the whole storage. And for figure 3, which is another day when we observe the storage, they are only like partially filled. So what the data that we need is to retrieve all this water area within each of this storage across a long time. So the disadvantages of this old method is that it's quite slow in processing because it has to handle all of these polygons with tons of vertices across a really long time and also a very big area. And it can also be very costly with the expenses. So the solution we came up with is a raster-based process in Google Earth Engine. So a bit of background of Google Earth Engine, if you are not familiar with it. So the Google Earth Engine provides with a web-based code editor, which was used during our development time. And it also provides JavaScript and Python APIs. It contains multi-petabytes data sets and also planetary scale analysis capabilities. And they are distributed processing, so the analysis can run parallelly in a cloud environment. So now we will be going through this raster-based workflow. So before we get started with the processing, we will need some prerequisites here. So the first prerequisite is that unfarmed water storage base layer. And we need to buffer and rasterize and also label each of the storage within this unfarmed water storage base layer. What we are seeing from figure 1 there, so the orange shaded area is the original storage, one of the storage, and we buffer it with a 10-meter buffers, which are shown in the blue shaded area. And the buffer we added here is to incorporate with the georeferencing arrows. And after buffering it, we we're going to rasterize it, which is to convert them from polygon to raster. To pixels, which are shown in the figure, which is shown in figure B, and so then the next step is going to label them. So the purpose of this label is that in order to flag them with pixel values, so we could process further, we labeled each of those storage with some special pixel values, and these special pixel values, they are all 5 multiples. So I have an example here. The OFS you are looking at is number 1227, and the special pixel value we have assigned to it is 6135. And in order to present this more like simply and more easily, is I have a very highly simplified image here to represent how it looks like. So just imagine this entire table that represents the base layer, and each of those grids represents one of the pixel. So what we are seeing here is we have OFS 1 to 6, and so for OFS number 1 has a special pixel value of 5, and the list continues. And for OFS number 6, we have a special value of 30. And in addition to this prerequisite, we also have to have 3 dictionaries. So the first dictionary should keep the OFS unique ID and its corresponding labels. And the second dictionary will keep the OFS ID and the label value plus 1. So if you are looking at the data we are showing up here, you can see that in the OFS dictionary, the first OFS ID has a pixel value of 6110, but in the water dictionary, it has a label value of 6111, which is plus 1. And also the third dictionary would be the OFS ID with their label value minus 1. Then we're going through the real data process. So the first step is, of course, to acquire all the optical satellite images that we can find from Google Earth Engine, which contains Landsat 5, 7, 8, 9, and Sentinel-2. And the second step, we're going to mask the cloud and invalid pixels. And after the masking, we're going to calculate the MNDWI, which is the index to tell us if it's water or not. So we're going to calculate the MNDWI for each of the pixel, and we're going to threshold it to generate a binary map. So if we find the pixel is covered by cloud, or if it's low quality pixel, we're just gonna assign the pixel value with minus 1. And if we find the pixel is covered by water, we identify it as water, we're just going to assign a pixel value of positive 1. And for the other, we just leave them blank. At the same time, we still have our OFS base layer, and we're just going to add these 2 layers pixel by pixel together. So you will generate an overlay layer which has all these values like 6, 4, minus 1, or 26, or 30, and all of that. And the next step is we're going to use this overlay layer and to identify which storage were affected by cloud that should be removed, not removed, the data should be removed, and also which data should be kept. So the first step is to confirm the cloud affected storage. Any water pixel that shows a pixel value of 5 multiples minus 1, which such as like 4 or 9, 14 or 19, their OFS ID will not be kept for that day's observation. So you can see that these 3 areas has been emptied. The data has not been kept because we have a value of 4 or 9 or 29 on that day, which means that these storage has been affected by the cloud, and we don't want to keep them. The second step is to confirm the actual water storage, which means that any pixel value that shows a value of the 5 multiples plus 1, like 6 or 11, 16 or 21, they will be retained, and the pixels will be flagged as actual water. And we have a final step, which is to confirm the empty storage, because there are some time that the storage is licensed and they are shown on the unfarmed storage base map, but on the day that we observe it, there's no water in there. It's fully empty. So any pixels that shows a value of 5 multiples their corresponding OFSD will be kept, and its area will be recorded as 0. So it's quite simple. So we will have our final result layers, which only the OFS number 3, number 4, and number 5 have been kept. And we will also record their pixel count, which for each one of them are 2 pixels, 4 pixels, and 0 pixels. And because we know that for each pixel, the area was 100 square meter, so we will know that the OFS area on that day for that specific storage was like 200, 400, and 0. So here is it's a preview of our final results. We will keep also the system time, which is when the satellite passed our region of interest, and the OFS unique ID and how many pixels are counted within that storage, and also their corresponding area. And we also kept the satellite tiles for easier further processing. So the advantages of this method, first of all, is only the area values from cloud-affected on-farm water storage is removed, not the entire cloud-affected satellite images. And I'm not sure if you are aware that Landsat 7 has been affected by some scanning law issue for a long time. I think it's 7 or 8 years. And in most of the current data set about this, like water storage and kind of water storage, they just like ditch all those images at all, but we didn't do that. We kept every single one of those images, and we only removed the data from the affected storage. So we have much more data compared to other data sets. The second advantage of this is it is very cost-saving and very rapid, because it avoided processing tons of polygons with many vertices, and it can work with a very large spatial temporal scale. So for retrieving like over 35 years of historical data that we have, well, it only takes about 1 hour. And the third advantage of this is this workflow is automated within the Google Cloud Platform environment. So I've set up a scheduler to trigger the cloud functions where we embedded the entire workflow in, and it can reproduce and export the results on a regular time basis to the cloud buckets. I think our clients now set up this regular time as 2 weeks. So in every 2 weeks, they will get some new data feed into their database, but you can even set it up to run it every day, so you will have a very near real-time results coming up. And the fourth advantage of this is it's very transferable to applications in any other area, and also in any similar workflows required. And also our clients is now using this method to retrieve the water area change for the natural water bodies. All they need to change is only the base layer. So you have changed the on-farm water storage base layer to the natural water body base layer and run the workflow again. It will give you all the results over 35 years within 1 hour again. And that's all. Thank you. Any questions?